Hello, beta. Good evening.
Good evening, sir. Good evening, sir.
Good evening. Good
Good
evening,
evening,
beta.
sir.
Good evening. Good evening. So, how are we today?
Good, sir. Good.
Okay, very good. Okay, so most of the people have joined in. So, beta, today we will be going into magnetic compass. We had touched upon the basic magnetism fundamentals for a short presentation. So we will now proceed ahead. We will complete the Earth's magnetism. One portion in Earth's magnetism is remaining. That is the dip angle, which is also known as the magnetic latitude. So I will show you that. After Earth's magnetism, we are going into ship's magnetism. We see different type of structures having different types of magnetism on the ship. So that is what we are going to see next. And after this, the next topic would be coefficients. So there are total 5 coefficients in magnetic compass, A to E, A, B, C, D, and E. So one by one, we will be going into those coefficients. So that's the plan for today. So ready, beta?
Yes, sir, can you provide magnetic PDF for exam purpose, sir?
Okay, I will. What do you want, beta? You want the notes?
Yes, sir. Short notes if available.
Okay, because beta, जो base book है, that is the magnetic compass by Captain Joseph and Captain Revari. So you should have that book. Now, if that book is very extensive, I will also give you some notes which are precise, concise notes which will be covering all the fundamentals. I will send you today after the class.
Okay, sir. Okay, sir. Thank you, sir.
Okay, beta. Okay. So ready, beta? Shall we start off with magnetism? Okay, all right. So let me put up the presentation. First, we will cover up the Earth's magnetism. So let me put it up. Okay, so this is the presentation which we saw on the first day also. Basically, I told you about two types of magnetism or two types of magnets. One are permanent magnets and the second one was induced magnet. So induced magnets are generated when a ferromagnetic material lies in the presence of a magnetic field. So then we saw two different poles of the magnets, red and blue pole. We saw that during induced magnetism, if the material is aligned with the magnetic field lines of the earth, it gets maximum induction. And if the ferromagnetic material is misaligned or at right angles to the magnetic field, to the inducing field, there is minimum induction or zero induction. Then after this, we saw that every magnet has two poles, blue pole and the red pole. Magnetic lines of force always come out from the red pole and they re-enter the magnet from the blue pole. We saw the two basic properties of magnets, like poles repel and unlike poles attract each other. And then we went into the Earth's magnetism. We saw that the Earth's magnetic field is exactly as if there is a bar magnet fitted inside the Earth. That's how God has made it. So the magnetic field of the Earth matches with the magnetic field of a short, powerful bar magnet which is fitted inside the Earth. So we saw that the magnetic poles of the Earth, they are not fixed and they keep on changing their location. And then we saw that this magnetic field of the Earth cuts the Earth's surface. The magnetic field lines cut the Earth's surface at different angles. And at the poles, this angle is 90 degrees. And at the equator, this angle is 0 degree. At the magnetic equator, magnetic field lines are parallel to the surface of Earth. And at the poles, magnetic field lines are perpendicular to the surface of Earth. So that's what we saw in the first presentation. So now moving ahead, beta. Let's repeat this particular slide, the magnetic poles and the magnetic equator, and continue. So moving ahead now. We can now see another diagram showing us the magnetic field lines of the Earth. Now, a very important aspect of these magnetic field lines is the angle at which they cut the Earth surface. We are aware that the south magnetic pole of the Earth has a red polarity and all magnetic field lines, they come out of it. And as you can see here also, in the southern hemisphere, anywhere you see the magnetic lines of force are coming out of the Earth's surface. We know the north magnetic pole of the Earth has a blue polarity and all magnetic field lines, they enter into that blue pole. And you can see everywhere in the northern hemisphere, the magnetic field lines are going into the surface of the Earth. A very important property which should be clear in our mind related to these magnetic lines of force is their angle of cut. Now, if you look carefully, these red color arrows represents the magnetic poles of the Earth. Now at the south magnetic pole of the Earth, you see these magnetic lines of force, they are coming vertically out from the Earth's surface. In other words, you can see they are making a right angle to the Earth's surface. They are perpendicular to the Earth's surface, or you can say the magnetic field lines are vertical at the location of the south pole. Now from the south pole, as you go towards the equator, you will see that the angle of these magnetic field lines with the Earth's surface starts to reduce. At the pole, this angle of cut between the magnetic field line and the Earth's surface was 90 degrees. As you move away from the pole towards the equator, the angle starts to reduce, maybe 80 degrees here, 70, 60, 50, 40. And as you go further and you come close to the equator, now at the equator, you will see that the magnetic field line's angle of cut becomes 0. The angle of cut was 90 at the pole. Coming close to the equator, the angle starts to reduce, and at the equator, the angle becomes 0. Angle becoming 0 means that these magnetic field lines are parallel to the Earth's surface. Now, as you move towards the north magnetic pole, again the angle starts to increase. Now the lines are going into the Earth's surface, but the angle starts to increase, maybe 10 degrees here, 20, 30, 40, 50, 60. And when you reach at the north magnetic pole, the angle of cut between the magnetic field lines and the surface again becomes 90 degrees. You can see at the north magnetic pole, the lines are again perpendicular, making a 90-degree angle to the surface of Earth. Now this angle is known as the magnetic dip or a magnetic dip angle. It is also sometimes called as the magnetic latitude of a particular place. You can see at the magnetic equator, this angle was 0. So the magnetic latitude of that place was 0. As you move towards the pole, the angle is increasing. Magnetic latitude is also increasing. And as you reach at the pole, the angle of cut becomes 90 degrees. The magnetic latitude at the pole also becomes 90 degrees. Another important thing which you will see from the diagram is you have the geographic poles also represented by the dotted lines. And we have the magnetic field lines also. We have the geographic equator also. Geographic equator is a great circle exactly midway between the geographic poles. You can follow the laser pointer. It shows the geographic equator now. This geographic equator is a perfect great circle. It follows geometry and it is a perfect great circle. Whereas the magnetic equator is not a perfect great circle. Magnetic equator is represented by this curved line. It is not a perfect great circle. The reason being magnetism is a dynamic property of the Earth. So it is not a perfect great circle, but a curved line. Now using the angle of dip or the angle of cut between magnetic lines and the surface, we can define the magnetic poles as well as the magnetic equator. Let us see what is the definition of magnetic poles. Magnetic poles are defined as those points where the Earth's magnetic field lines are vertical or they are perpendicular to the Earth's surface. As you can see in the diagram, at the location of the poles, the magnetic lines of force represented by red arrows are perpendicular to the Earth's surface. They are making a 90 degrees angle. Moving ahead now, beta. And using the same dip angle, now we can also define the magnetic equator. The magnetic equator is an imaginary line on the Earth's surface, joining those points where the Earth's magnetic field lines are horizontal or parallel to the Earth's surface. So you can see at this particular point here, the magnetic field line is parallel to the Earth's surface. The Earth's surface is in the up and down direction here. The magnetic field line is also in the up and down direction here. The field line is parallel to the Earth's surface. And if we join all these points on the Earth's surface where the magnetic field lines are parallel, this creates or this marks the magnetic equator.
Sir, parallel
now, as this
means basically where the angle is 0, right, sir?
That's correct, beta. The points joining the dip angle 0 will join together to form the magnetic equator.
Okay, sir. Thank you, sir.
Discussed earlier, the angle at which the lines cut the surface of Earth is known as the dip angle, and this diagram shows the dip angle very clearly. You can see the angle of cut between the magnetic field lines and the Earth's surface at all the locations. Let us now see the definition of the dip angle. This angle which the Earth's magnetic field makes with the Earth's surface or the horizontal is known as the dip angle. As we can clearly see in this diagram, the dip angle is 0 at the equator and is maximum 90 degrees at the poles. Moving ahead now. Now this dip angle can be measured using an instrument which is known as the dip meter. The dip at any place can be observed using an instrument named as the dip meter or a dip needle, which you can see in the diagram. Now in this dip needle or a dip meter, you see we have a magnetic needle, and this magnetic needle is free to swing in a vertical plane. There is an axis or swivel at the center here, and this magnetic needle is free to swing or move in the vertical plane. There is a scale which is provided. The scale gives us the dip angle. Like right now you can see that the dip angle is being given as, you can see 10, 20, 30, 40, 50, 60. The dip angle which is shown here is close to 64, 65 degrees. The needle is free to swing in the vertical plane. And when we use this instrument is first aligned in the north-south direction using a compass. And once it is aligned to the north-south direction, this needle is usually locked initially in the horizontal plane, and as soon as you remove the locking, the needle swings up and down and settles down, showing us the dip angle. Let me show you a video where a practical dip angle calculation is being done. Let me show you, beta. Give me a minute. Okay, so you will see how a dip meter is practically used to obtain the dip angle.
A dip is, or the inclination, is how much below the horizontal the magnetic field points. And so we need a special type of compass, a dip compass or dip meter, to get that information. So currently the needle can move around in that plane, and will align the rotation axis of the dip meter with the compass needle, such that 0 degrees is at the north end of our magnet. Then I can rotate this 90 degrees, and the needle can oscillate and move in this vertical plane. The dip angle is defined from -90 to +90, with positive dip being a measure below the horizontal. So you and all of your group mates should find a dip meter measurement, each person going through the entire process.
Okay, so I hope that makes it clear, beta.
They align it with the north and south magnetic field lines.
No, beta, it is basically the needle has to be first aligned in the north-south direction. Okay.
And this is pointing compass north or magnetic north?
Okay, let me show you. You see, first they have kept the needle which is free to swing in the horizontal plane. That's how they have kept it. Right now, the needle is free to swing in the horizontal plane. Right, beta?
Okay, sir.
Now what they do is they align this needle to 000180 marked on the circumference. So that's what they will do now. Let me stop the voice. So you see now they are aligning it, and at this moment now you see the needle is perfectly aligned with 000 and 180 markings on the round circumference, right, beta?
Okay, sir.
Now, after this, they will turn the needle and it will become free to swing in the vertical plane. At the moment, it is free to swing in the horizontal plane. It is exactly acting like a compass.
सर ये कंपास मतलब वही अपना नॉर्थ पोल नहीं है ना, मैग्नेटिक नॉर्थ पोल है ना?
Yeah, that's right. The compass
sir.
needle
ठीक है
always
सर.
points towards the magnetic north. So
हाँ, ठीक है
once
सर.
the needle is aligned, now you rotate it by 90 degrees and make the needle swing in the vertical plane. Now, as soon as
ठीक
you
है सर.
make the needle free to swing in the vertical plane, it aligns with the magnetic field lines of the earth and shows you the dip angle.
ठीक है सर, अंडरस्टूड. थैंक यू.
Okay, beta. So this is turned by 90 degrees. The needle now becomes free to swing in the vertical plane. And as you make it free in the vertical plane, it will align itself with the magnetic field lines of the earth. So you can see now the red end of the needle is pointing downwards, the blue end is pointing upwards. Can you tell me, beta, whether this experiment is being done in the north hemisphere or south hemisphere? Can you judge?
North only, sir. Looks north. North hemisphere, sir. North.
Very good, beta. That's north hemisphere. Because you see, when I showed you the earth diagram, the north hemisphere has the earth's blue pole. And that blue pole attracts the red end of this needle. Okay. If it was south hemisphere, the red would be pointing upwards and the blue would be pointing downwards. Okay, great. So closing down this video now, going back to the presentation, beta.
Sir, in this experiment on that needle, there is no effect of the gravity, sir.
Beta, this needle is very, very light. The needle is very, very light. Of course, there will be some effect, but since it is a powerful magnet, the effect of gravity can be easily neglected.
Yes, sir.
Okay. Let's go back to the presentation. Okay, beta. Great. So we have seen the dip meter. Let's move ahead. We now have another diagram showing very clearly the magnetic field of the earth as well as the dip being recorded by a dip needle. You can see this is the earth surface. We can see the magnetic lines of force. The arrows show the direction in which they are going. In the southern hemisphere, they are coming out of the earth's surface, and in the northern hemisphere, they are going down into the earth's surface. This is the short bar magnet assumed to be fitted inside the earth, and you can see this is a magnetic equator. If we have a dip needle placed at the magnetic equator, the dip needle pointing in the direction of the magnetic lines of force will be parallel to the earth's surface. It will be horizontal, showing us the dip as 0. Now, as we proceed towards the North Pole, at this particular location, the dip needle again aligns itself with the magnetic lines of force, and you see the red end of the dip needle will now be attracted by the blue end of the Earth's north magnetic pole, and it will show a downward dip. As we keep moving closer to the North Pole, this dip angle starts to increase. It keeps on increasing, and as we reach exactly at the North Magnetic Pole, you see the magnetic lines of force are vertical here, and the dip needle will be pointing exactly downwards. The red end of the dip needle will be pointing exactly downwards towards the blue end of the Earth's North Magnetic Pole. You can also see the geographic North Pole. It is at a different location from the magnetic North Pole. So you can see the dip angle starting from 0 at the magnetic equator, increasing and going up to 90 degrees at the magnetic pole. Now we have understood that the magnetic field lines cut the surface of Earth at any particular angle from 0 degrees to 90 degrees depending upon the location. We have selected a particular location on the Earth's surface where the magnetic field lines are in this particular orientation. They are going down into the surface of the Earth, so that tells us that this is the northern hemisphere, and they are making this particular angle. This is the dip angle. So the angle of the magnetic field lines with the horizontal or with the surface of Earth is the dip angle. You can see the dip angle here. Now the magnetic field in this particular direction is represented as total field intensity of the Earth's magnetic field. Now this total field intensity or the magnetic field of the Earth is broken down into two components for our use, for our utility to understand the magnetism better. These two components are, one is the horizontal component, which is known as H or HF, a short form for horizontal force. This horizontal component of the total magnetic field of the Earth, which is known as H or HF, is what makes the compass point towards the magnetic poles. This H or HF basically provides the directive force to our compass. The H or HF horizontal force is maximum at the equator, as the magnetic field lines at the equator are perfectly horizontal, and the H component reduces with the increase in latitude of the observer, becoming nil at the magnetic poles, because the magnetic field lines at the poles are perfectly vertical, making the horizontal component 0. Therefore, the directive property of a magnetic compass, which is based on or dependent upon H or HF, the horizontal component, is highest at the equator and starts to reduce when the vessel proceeds towards the pole, eventually becoming nil at poles. This is exactly the reason that as we move into higher latitude, the magnetic compass starts to lose its directive force. After we cross a latitude of 70 degrees north or south, going towards the pole, the compass becomes highly unreliable. The other component of the total field intensity of the Earth, which is the vertical component, is known as Z component. Now, as we have discussed under the dip angle, this Z component will be acting downwards in the northern hemisphere, and this Z component will be acting upwards in the southern hemisphere. In the northern hemisphere, the magnetic field lines go down, so the Z component acts downwards. In the southern hemisphere, magnetic field lines come up from the Earth's surface, so the vertical Z component acts upwards. This Z component or vertical component does not affect the directive property of our compass in any way. It does not enhance or does not diminish the directive property of the compass. This Z component, however, affects the magnetism of the ship, which we will discuss under the head of ship's magnetism. Clear, beta? Any doubts coming in?
ये डायरेक्टिव कंपोनेंट मतलब बेसिकली नॉर्थ मैग्नेटिक पोल और साउथ मैग्नेटिक पोल की बात कर रहे हो आप?
Yeah, that's correct, beta. The H or HF is basically the horizontal component which provides the directive force to our compass. Our compass needle is also free to move in the horizontal plane. So the stronger this horizontal component is, the easier it will be for the compass to point towards north. जैसे जैसे ये H component weak होता जाएगा, हमारी कंपास की डायरेक्टिव फोर्स भी लूज होती जाएगी.
ठीक है सर, ओके.
Okay, great. So this was Earth's magnetism, beta. Now we are going into the ship's magnetism. So I'm closing down this presentation. Okay, so let's go into the ship's magnetism. Now let's move into the ship's magnetism. We have already discussed about the Earth's magnetism. Earth's magnetism is what affects our magnetic compass and provides the directive force to the compass. Now, ship's magnetism is another force which is very much present at the compass location and it affects our compass. So we are going to analyze what type of magnetism is present in the ship and how does that magnetism of the ship affects the compass in a positive way or in a negative way, and eventually in the end we are going to see how do we counteract or compensate the effects of the ship's magnetism on our magnetic compass. So let's go into these concepts one by one. Now, in the olden days, the ships were made of wood. Wood was a non-magnetic material and would not have any magnetism of its own. On such a ship, the only force which affects the magnetic compass is the Earth's magnetism, and the compass would point in the direction of the magnetic poles. Once we identify the magnetic poles, if we apply the variation, we can easily find out the direction of the geographic poles also. So things were pretty straight and simple. But nowadays, ships are being built of steel, which is a ferromagnetic material. Steel or mild steel or iron is a ferromagnetic material and it has the capability to acquire magnetism. We have seen in the previous slides that two types of magnetism can be generated in ferromagnetic substances. One is permanent magnetism, which was generated by bringing it in contact with a permanent magnet in a specific way. And the second was induced magnetism, which is generated when any ferromagnetic material comes under the effect of a magnetic field. So this mild steel, being a ferromagnetic material, can acquire magnetism of its own. And as we have already discussed, the acquired magnetism by the ship, by the steel of which the ship is made, could be either induced magnetism or it could be permanent magnetism. So these are the two types of magnetism which could be present in the ship structure. Now, based on what type of magnetism is acquired by a particular structure or part of the ship, it is divided into two types. All the structures are divided into two categories. The first category is known as soft iron structures, and the second category is known as hard iron structures. Let us see them one by one. Induced magnetism of the ship is acquired by those parts of the ship or steel structures which instantly and easily get magnetized when placed in a magnetic field. Also, they immediately lose their magnetism as soon as the magnetic field is removed. These type of materials or structures are termed as soft iron structures. Now moving on to the hard iron structures. Permanent magnetism of the ship is acquired by those parts of the ship or steel structures which offer substantial resistance to magnetic changes. These materials do not get magnetized easily, but once magnetized, they retain their magnetism permanently. Now, these kind of structures or these type of materials are termed as hard iron structures. So basically the ship is divided into these two kinds of structure, the soft iron and hard iron structures. Soft iron structures gain or acquire magnetism very easily, and that acquired magnetism is induced magnetism. It is temporary in nature. As soon as the inducing field or the magnetic field which was responsible for the magnetism is removed, the structures lose their magnetism instantly. Whereas on the other hand, the hard iron structures, they do not acquire magnetism easily. Just the presence of magnetic field is not sufficient to acquire magnetism in those structures. But if they get magnetized, then the magnetism remains there permanently. They do not lose their magnetism easily. Now, one more thing to understand before we proceed ahead. It should be very much clear in your mind that these hard and soft words which we have used in the definitions, hard iron structures and soft iron structures, they are basically denoting the two different types of structures or material having different magnetic properties. They relate to their magnetic properties or magnetic behavior. And these materials are not literally hard or soft to touch. Both of them are made up of steel, iron, so they are equally hard or soft to touch. It is not that a soft iron structure is very soft to touch. No, it is not that way. Do not take the meaning of the words literally. They are just denoting their magnetic properties or magnetic behavior. Clear up to here, beta? Any doubts? Very good, beta. So going a little more further into the hard iron and soft iron, although no structure on the ship can be categorized as entirely or 100% a hard iron structure or a soft iron structures, because any structure on board a ship will possess both the properties in varying degrees. Some part of it will acquire magnetism very easily and lose it equally easily, and some part of the structure will acquire magnetism very slowly, and once acquired it will not leave. So if every structure has both these properties in it, how do we classify them as hard iron and soft iron? Now these are generally classified on the basis of which out of the two magnetic behavior is predominant in that structure. Let us say we have a particular structure. Let us say we have a mast. Now in that mast we analyze and find out that 70% of it has soft iron magnetic properties and 30% acquires or has the hard iron magnetic properties. So since predominantly most part of it is a soft iron magnetic behavior part, we will term the mast as a soft iron structure. The ship structures which are generally prefabricated, means they are made in the factory or made in the yard and fitted on board in situation. These structures could be the transverse beams, the fore and aft longitudinals, the vertical stiffeners, the mast, the funnel. All these kind of structures, if you see a ship being built in the yard, you will see that all these structures, the beams, the longitudinal, vertical stiffener, mast and funnels, they are basically prefabricated in the yard. They are picked up by a crane, brought to the place where the ship is being constructed, and they are held in place and they are welded there. So these kind of material which are prefabricated, predominantly exhibit soft iron magnetic behavior. On the other hand, the ship structures which are extensively worked upon. By worked upon, we mean when the ship is being built, there's a lot of welding or heating or hammering, bending, grinding, cutting. These kind of processes are being made or carried out on those structures. These structures could be the ship's hull, they could be the bulkheads, they could be the decks. Now these kind of structures predominantly exhibit hard iron magnetic behavior. Clear up to here, beta? Any doubts? Very good, beta. Now we are going further into the soft iron and hard iron structures, because this is a very important concept to understand the working as well as the correction of the magnetic compass. The soft iron structures which are present on board, they can be classified into two different categories. These are the vertical soft iron, which has a vertical orientation. It could be the vertical stiffeners. The vertical stiffeners are welded onto the bulkheads, so they have a vertical orientation. Or you could have the masts, forward mast, any cranes, the crane houses, the aft mast, and you have the funnel. All these structures have a vertical orientation on board. The second type of soft iron structures could be horizontal soft iron structures. Now horizontal soft iron structures could be the fore and aft longitudinals. It could be the athwart ship beams. Both the longitudinals as well as the beams are welded on top of the decks or top of the keel plate or at the bottom of the, you can say the top deck of the tanks. So they have a horizontal orientation. So these are the two different categories into which the soft iron is divided. In short, the vertical soft iron is also known as VSI, and the horizontal soft iron is known as HSI. Moving ahead now.
Sir, how this funnel is vertical soft iron?
Beta, the orientation of the funnel is in the vertical direction, and you will see that during shipbuilding, funnel is usually prefabricated and brought on the ship. So usually the crane will pick up the entire funnel structure. They will bring up where the ship is being built and they will weld it in place. So it has predominantly soft iron properties and its orientation is a vertical orientation.
Okay, sir.
Okay. Now, if you consider a horizontal soft iron, as I told you, a horizontal soft iron could be a fore and aft longitudinal or a athwart ship beam. The horizontal soft iron structures on board are magnetized by the horizontal component of the Earth's magnetic field known as H or HF. Now, when we discussed the magnetic field of the Earth, in that we discussed that at any particular place on the Earth's surface, the total magnetic field intensity represented by this slanting vector can be divided into two components. The horizontal component known as H or HF and the vertical component known as Z. Now, why have we divided them into components? So that we can understand the effect of Earth's magnetism easily onto the ship structure and onto the compass. Now, obviously, if you have a horizontal soft iron structure on board, it will be magnetized by the horizontal component of the Earth's magnetic field, that is H or HF. Now, how is it affected? Now, a blue pole is acquired where the lines of force enter the material, and the red pole is acquired where they leave the material. Now we have seen this, that every magnet has its two poles, the blue and the red pole, and we have seen red pole is the one from where the lines of force come out, and blue pole is the one where the lines of force enter into the magnet. So same thing applies here. Let's assume we have a ship which is on a northerly course, 000 course. The ship is at the equator. Now, if you visualize a ship on equator on a heading of 000, you will see that the magnetic lines of force at the equator, they are also parallel to the Earth's surface. They are also horizontal, and they will be entering from the stern of the ship, and they will be leaving from the bow of the ship. Now, if we have a fore and aft longitudinal, the magnetic lines of force will be entering into that end of longitudinal which is toward the stern. And since the lines are entering there, it will have a blue pole at that particular location. Going to the forward end of the fore and aft longitudinal, the lines of force will be coming out from the forward end. So the forward end of the longitudinal will acquire a red polarity. So this is the meaning of the second sentence. A blue pole is acquired where the lines of force enter the material, and a red pole is acquired where they leave the material. Now the strength of induced magnetism generated in a longitudinal is a horizontal soft iron structure. So when it is exposed to the magnetic field of the Earth, it acquires magnetism. But the strength of the induced magnetism depends on the heading of the ship. Let's understand this by taking this example. Now we know that the H component, the horizontal component of the Earth's magnetic field, always acts northwards. So therefore, the horizontal soft iron structures will receive maximum induction if they lie in the north-south direction. And they will receive zero induction if they lie in the east-west direction. You remember when we discussed about the induced magnetism, I told you that the strength of the induced magnetism depends upon the orientation of the soft iron. If the soft iron structure is oriented or aligned in the direction of the magnetic field, maximum induction would occur. And if it is misaligned, that means it has a orientation perpendicular to the direction in which the field lines are going, it will have minimum or negligible induction. So taking this example, we had a vessel heading in the northerly direction. So a vessel which is heading north, the fore and aft longitudinals, which will also be lying in the north-south direction, will receive maximum induction from the magnetic field of the Earth. The Earth's magnetic field also is in the north-south orientation. So they are perfectly aligned with the magnetic field of the Earth, generating maximum induction. So with maximum induction, it will have strong magnetism acquired. And if you now concentrate on the outward ship beams, our vessel is heading in a northerly direction. So the fore and aft longitudinals were perfectly aligned with the magnetic field, but the outward ship beams on that ship will be oriented in a east-west orientation. Now the magnetic field of the Earth is going in a north-south direction. The outward ship beam oriented in a east-west direction. So they are at right angles to each other. So totally misaligned with the magnetic field of the Earth. So this tells us that there will be zero or negligible induction on the outward ship beams with the ship lying in the northerly heading. So a ship is on the northerly heading, the fore and aft longitudinals will have maximum induction and the outward ship beams will have negligible or zero induction. Is that clear, beta? Any doubts up to here?
I just want to understand. Like you said, the soft iron will be softer because they are built separately at a workshop, but they are also being worked upon. They are being also exposed to a lot of hammering and welding at not at the ship side, but at some of the workshop. So why don't they get the?
Okay, all right. Okay, let's take the example of a longitudinal beta. Now, if you visualize a longitudinal, you see a longitudinal is made in the foundry. It's made in the foundry, then it is brought to the yard and it is cut to size. And after cutting it, it is welded with a single welding seam. So yes, there is a little bit of welding which is involved, but the magnitude of working upon which is done on a longitudinal is much lesser. If you compare this longitudinal with a deck plate or a keel plate or ship's hull plate, you will see these plates are built in the foundry, but when they are brought to the yard, first they have to be brought into shape. The hull of the ship is curved, so they have to be bent in that curved orientation. It's a 3D kind of bending. After it is brought close to the ship, toward the ship hull where it is ready to be welded, you will first weld it with a single welding seam. You may require further bending of the plate using hydraulic jacks and all to bring it in complete shape. Then you will be welding longitudinals on top of it. You will be welding vertical stiffener on top of it. So the working upon which is done on a hull plate or a deck or keel plate is much more compared to what is done in a longitudinal. So yes, you are right that there is some amount of working upon which is done on a longitudinal also. Obviously, you will have to weld it to the ship's hull. But the amount being very less, it shows a predominant behavior of soft iron. So does that make sense, beta?
Yes, sir. So it depends on the magnitude of work done.
Exactly, beta. That's right. If you have a structure, you say, sir, 60% of it has soft iron properties and 40% hard iron properties. Now, I cannot put it in, you see, I cannot put it in between the two structures. I will have to classify it as hard or soft. So any percentage of soft iron more than 50 will put it to a soft iron category.
Okay, sir. Understood. And sir, one more thing.
Yeah.
So the parts which are added to the ship later on will have more acquired magnetism compared to the parts which were added in the initial phase of the building.
No, I didn't get you. Can you explain?
So like, okay, we started building a ship. We started with a keel. And then coming from bottom to up, we're coming up and introducing the parts in it. So the parts which are added to the ship later will have more magnetism as compared to the parts which were added in the initial phases of the ship building.
Okay. Why more magnetism, beta, in the later parts?
Because then it will have the effect of magnetic fields of permanent magnets also or hard irons which are already present there.
Okay, beta, वैसे तो it does not make much of a difference whether you add a structure in the initial stages or the later stages. It does not make much of a difference. But if you compare them, going minutely also, the structure which are added first of all, the first structure will be the laying of the keel. The structure which are added first of all, those structures have more magnetism because those structures will be spending more time in the yard and it will be affected by the Earth's magnetic field in that orientation. If the ship takes 6 months to build, the keel will be exposed in that particular yard to the Earth's magnetic field for those complete 6 months, whereas the deck plate may be exposed only for 3 months. So the more time a particular material is exposed to the ship structure when it is being worked upon, the more permanent magnetism it acquires. But that only relates to the hard iron magnetism. Soft iron, whether it is put in the ship in the initial stages or the later stages, will have no effect at all. Both of these structures will be equally magnetized.
Okay, sir. Understood. So basically, the Earth's magnetism will have always much more effect than the acquired magnetism of any other hard iron.
Yes, that's right बेटा. अभी हम सॉफ्ट आयरन डिस्कस कर रहे हैं ना, इसके बाद मैं आपको हार्ड आयरन भी करवाऊंगा. अब जो सॉफ्ट आयरन स्ट्रक्चर्स हैं, their magnetism is dependent upon the magnetic field at that particular instant. Now the ship is heading north. I will now in the next slide, I will change it to a easterly heading. And you will see as soon as I change it to easterly heading, the longitudinal is going to lose its magnetic property. And the outward ship will become very powerful magnet. So the soft iron magnetism is dependent on what is the heading of the ship, what is the orientation with respect to the Earth's magnetic field line. But the hard iron magnetism is dependent upon one, how much working upon is done, and for how much time it is exposed to the Earth's magnetism during working upon. The more it is exposed to the Earth's magnetic field, the more working upon which is done, it will acquire that much more permanent magnetism. And that magnetism is not going to change later on. It will stay with that structure for the entire life of the ship.
So, sir, in the dry dock, when we go for dry dock every 3-4 years, so that time also the magnetism, like it will acquire permanent magnetism because we are working upon.
Yes, that's right, beta. That's right. After every dry dock, you will see that the ship will be swung and the compass will be readjusted or recorrected. So this is exactly the reason why it is done, because the amount of steel which you have changed. Let us say you go to a dry dock and there is a huge amount of steel renewal which happens. The more the amount of steel you have changed, the more will be the difference or change in the ship's magnetism. The permanent magnetism of the ship is going to change that much. So a compass adjuster will have to come after the ship sails out. He will have to evaluate how much change in the magnetism has happened, and he will have to recalibrate the correctors.
Got it, sir.
Okay. मैं अभी करवाऊंगा आपको. We will go into hard iron also. As we move ahead, it will keep on becoming clear in your mind. So this was soft iron, and we had the ship on another lee heading. So let's change the heading and see what happens. Now from this, we are able to understand that the magnetism generated in the horizontal soft iron depends on the heading of the ship. We have seen this ship heading in the northerly direction. There was maximum induction in the fore and aft longitudinal, and there was zero induction in the athwart ship beams. You can imagine it in this way now. Let us assume that this particular ship, which was heading in a northerly direction, now changes its heading and alters its course, and now it is heading in the east-west direction. If the ship is heading in the east-west direction, you can now see that the fore and aft longitudinal is also lying in the east-west orientation, and it has become perpendicular to the magnetic field of the Earth, which is lying or running in the north-south direction. So when the ship alters course to 090 and is moving on a easterly track, the fore and aft longitudinal are going to lose their induction. There will be no magnetism or negligible magnetic field acquired or generated or induced magnetism generated on the fore and aft longitudinal. Now on the other hand, the athwart ship beam in this condition with the ship heading east, the outward ship beams are now lying in the north-south orientation. The Earth's magnetic field is also in the north-south orientation, so they are perfectly aligned with each other, generating maximum possible induction on the outward ship beams. Thus, the magnetism generated in HSI depends on the heading of the ship. Because as the heading of the ship changes, the orientation of the HSI with respect to the magnetic field of the Earth also keeps on changing. The induced magnetism generated in a vertical soft iron or a horizontal soft iron will also change with the position of the ship. Now you see the basic cause of this magnetism, the induced magnetism in soft iron structure, is the magnetic field of the Earth. Now if the ship changes its location, let's assume that the vessel was on the equator and now it has moved towards the pole. Now as soon as the vessel changes its location, the Earth's magnetic field, which is the generating force for inducing the magnetism, also changes. So as the vessel changes its position, the magnetic field which is affecting the vessel also changes. The magnetic field at the equator is in a different orientation. Field lines are horizontal. Horizontal component is the strongest. The zero component, the vertical component is the zero component. Now as you move towards the pole, horizontal component keeps on becoming lesser and lesser and vertical component keeps on becoming stronger. If you go at the pole, you have zero horizontal component and maximum vertical component. So with the magnetism of the Earth changing with position, as the ship goes from position A to position B, the induced magnetism in the ship's soft iron structure is also going to change. Now the induced magnetism in the ship's structure will also change continuously when the vessel is rolling or pitching. Now when the vessel is rolling or pitching, the fore and aft longitudinal or the outward ship beam or the vertical structures, they are also changing their orientation time and again. With every roll and with every pitch of the ship, the HSI and the VSI are going to change their orientation. And as their orientation changes, the induced magnetism in those structures also changes. Clear, beta? Very good. Let's move ahead.
Excuse me, sir.
Go ahead, beta.
Sir, in this we are saying this changing in the position that refers to the changing in ship's heading, right, sir?
Yeah, with the ship's heading change, the induced magnetism in HSI is going to change as we saw in these two diagrams. But also when the position or the location of the ship changes, equator to pole or pole to equator, when it changes, the location changes, even that will have an effect in the induced magnetism, beta.
Okay, sir.
Okay. Now we are aware that the horizontal component of the Earth's magnetic field, which is H or HF, this component is the maximum or the strongest at the equator, because 100% of the field, magnetic field of the Earth is lying in the horizontal orientation, making the H or HF very, very strong. And this horizontal component of the Earth's magnetic field is nil or zero at the poles, because at the poles, the Earth's magnetic field becomes vertical and it has a zero horizontal component. So this actually gives us an insight into the induction in the horizontal soft iron structures also. The horizontal soft iron structures will therefore receive maximum induction at the equator and zero induction at the poles. So if we have a ship at the equator, it will have maximum induction generated in the horizontal structures. If the same ship goes to the poles, those horizontal structures will lose their entire magnetism because the H or HF component of the Earth's magnetic field has vanished at the pole. Moving ahead now. Let's now move into the vertical soft iron on the ship, the VSI. Just as the HSI, horizontal soft iron on board, was induced by the H or HF component of the Earth's magnetic field, exactly in the same way, the vertical soft iron or VSI on board is magnetized by the vertical component of the Earth's magnetic field. The vertical component is represented by Z. Wherever the magnetic lines of force enter into the structure, it will acquire a blue pole, and wherever the lines of force leave a structure, it will acquire a red pole at that particular location. To give you an example, let's assume we have our ship now at the North Pole. If the ship is at the North Pole, the Earth's vertical component, Z component, is the strongest there. The magnetic field lines at the North Pole are going vertically downwards. So if a ship is standing on the North Pole, you will see that the magnetic lines of force will be going vertically downwards into the Earth's surface. Let's assume or visualize the mast on that particular ship. Let's assume the forward mast. Now with the vertical lines, the lines of force going vertically downwards, they will be entering from the top of the mast. Now this point where the lines of force enter, that is at the top of the mast, it acquires a blue polarity. Wherever the field lines enter into a structure or a magnet, a blue pole is acquired, and these vertical lines of force going downwards will be coming out from the base of the mast. So the bottommost part of the mast or the base of the mast, from where the magnetic lines of force are leaving or going out, gets red polarity. It acquires red polarity because wherever the lines of force leave or come out from a structure or a magnet, it acquires a red polarity at that location. Now let's assume that this same ship starts moving now. At the North Pole, the top of the mast was blue and the bottom of the mast was red. This ship has started traveling now, and this ship now has crossed the equator and gone into southern hemisphere, and it has reached the South Pole. Now the same ship is at the South Pole. We are aware that at the South Pole, the magnetic lines of force, they come out from the Earth's surface. Now when they come out of the Earth's surface, they will be entering the mast from the bottom, thus giving it a blue polarity. The bottom of the mast now acquires a blue polarity, and these lines of force will be leaving from top of the mast, giving it a red polarity. So you see, as we changed the hemisphere, with the change in hemisphere, the direction of the magnetic lines of force of the Earth also changes. In the southern hemisphere, they come out of the Earth's surface, and in the northern hemisphere, they go down into the Earth's surface. And with this change, the poles acquired by the vertical soft iron also change. The poles get reversed when the ship changes from one hemisphere to another. So it is mentioned in this last point here, positioning of the poles. That means whether the blue pole will be on top of a vertical structure or the red pole will be on top of a vertical structure will depend upon the hemisphere the vessel is in presently. Clear, beta? Any doubts?
सर ये सॉफ्ट वाले में भी we will have same poles ना, जो इक्वेटर की तरफ है that will have red, and जो forward north pointing, it will be blue.
Don't relate it with the equator. Relate it with the direction of the magnetic field lines. जहां पे भी lines enter करेंगी बेटा वो blue polarity लेगा और जहां से भी lines बाहर निकलेंगी वो red polarity लेगा.
ठीक है सर. ओके.
Okay.
So one question I have.
Go
As
ahead,
you
beta.
said, the ship when it moves and when it changes from one place to another, like you showed in the example that the polarity is changing. So
Right.
it affects the ship's magnetism.
Right.
So how like when we are making a deviation card or we are correcting putting the corrector magnets at one place is
Right.
applicable for other places like here the polarity is changing, so ship
Okay.
magnetism will change.
Very good बेटा. Excellent. Great. देखो मैं बताता हूं तुम्हें. अब बेटा हमने देखा कि जो अर्थ का मैग्नेटिज्म है वो तो हमारे शिप को डिफरेंट वे में अफेक्ट कर रहा है. सो शिप्स मैग्नेटिज्म इज चेंजिंग कंटिन्यूसली एज यू मूव फ्रॉम इक्वेटर टू पोल्स और यू चेंज योर लैटिट्यूड, यू चेंज योर हेमिस्फीयर, शिप्स मैग्नेटिज्म इज गोइंग टू चेंज. अब बेटा हम इस चीज को करेक्ट करने के लिए जो करेक्टर लगाएंगे ना, दैट करेक्टर ऑल्सो विल बी ए सॉफ्ट आयरन करेक्टर. So this is one of the principles which we follow in magnetic compass correction. A soft iron deviation is corrected using a soft iron corrector. So when the ship changes its location, the corrector which is a soft iron corrector and it is also being affected by the Earth's magnetic field, its correction will also change. So जैसे शिप का मैग्नेटिज्म चेंज होगा वैसे ही हमारे करेक्टर की पावर भी चेंज होगी and at every latitude it will keep on matching or compensating the effects of ship's magnetism. Right,
Okay,
beta?
sir. Understood. Yes, sir.
Okay.
Clear.
This is one of the principles which we follow. Hard iron or permanent deviations are corrected using permanent magnets, and soft iron or induced magnetism deviations are corrected using induced magnets or soft iron. So जब मैं कोफिशिएंट्स में जाऊंगा तो आप देखोगे कि जो उसका कॉज है हम उसी करेक्टर के साथ उसे रेक्टिफाई करेंगे. Okay, great. So let's go back to the presentation. Okay, beta, let's move ahead. Now we are aware that this vertical component is the strongest or maximum at the poles and it is nil at the equator. Therefore, the vertical soft iron structures will receive maximum induction at the poles and zero induction at the equator. Moving ahead. Now moving further to ship's permanent magnetism. Till now we have gone in detail and understood the induced magnetism of the ship, which is acquired by the soft iron structures. We have seen their relationship with the heading of the ship, with the position of the ship, whether the ship is on the equator or at the pole, southern hemisphere, north hemisphere, horizontal soft iron and vertical soft iron in detail. Now we move on to the ship's permanent magnetism. The permanent magnetism in the hard iron structures of the ship is acquired during shipbuilding, during the building of the vessel in the shipyard. Now to give you an idea about this, you see in this diagram, this ship is made fast to the berth or at a yard or a dock, and it is situated in this particular orientation. The ship is being built in this particular orientation, and the pink color arrows which you are seeing, they basically represent the magnetic field of the Earth. The vessel is in northern hemisphere. That's why you see all these lines are going into the surface of the earth. And the angle at which they are cutting the surface of earth is the dip angle at that particular place. So the ship is exposed to this particular magnetism of the earth's magnetic field. The hull of the ship will lie in this position till the time the construction of the ship is complete. In a yard or in a dock, when you start the shipbuilding, laying down the keel of the ship remains in the same orientation till the time it is ready to be launched for sea trials. So the Earth's magnetic field will keep on affecting the ship in this particular orientation only. So you can see the magnetic field lines are entering from the top deck of the ship and they are leaving out from the keel of the ship. So the hull of the ship lies in one constant direction and is worked upon. When the ship is being constructed, we will be welding the plates, we will be hammering them, bending them, heating them. A high voltage electric current will be passing at the time of welding. So we will be using grinders, cutters, all these instruments on them. So all the ship's plates which are being fitted will be worked upon at the time of shipbuilding. Now during this entire process, which happens over a long period of time, it may take 1 year or it may take 6 months for the ship to be built. So during this long period, the Earth's magnetic field continuously acts on the hull in the same direction or the same orientation. Now, since we are working upon all these metal plates which are being fitted on the ship, and the Earth's magnetic field is acting on it in the same orientation, it generates permanent magnetism in these hard iron structures. So I told you that hard iron structures are those structures which are extensively worked upon at the time of construction of the ship or shipbuilding. Like say for example a keel plate, a deck plate, a bulkhead. Now when you are fitting this, let us assume there is a deck plate, you are fitting this deck plate on the deck of the ship during its construction. Now you will be cutting the plate, making it to size, you will be bending it as required, you will be hammering it, then you will be welding from the seams, then you will be welding a stiffener or a longitudinal on it or a transverse beam on it. So all these things, when they are happening and we are working upon this particular deck plate, the Earth's magnetic field is acting on that deck plate in one particular orientation. And this Earth's magnetic field acting on it during all this jobs or work being done generates a permanent magnetism in these structures. Since a lot of working upon is being done, they are hard iron structures, and the Earth's magnetic field generates a permanent magnetism in these hard iron structure. Now, as this is a permanent magnetism, once the material acquires it, it will not then change with time or with the position of the ship. The permanent magnetism once acquired remains there in the structure and it will not change with time or when the ship changes its position. So is that clear, beta? Any doubts? Very good, beta. Great. Now, since it is permanent magnetism, the poles which are generated, as we have seen, a blue pole is generated where the lines enter the material and a red pole is generated where they leave the material. The poles generated are also permanent. The course or the heading of the ship or the rolling pitching motion of the ship will not have any effect on them. Once these poles are generated, the rolling pitching of the ship, the course of the ship, the heading of the ship, the position of the ship will not have any effect on these poles because these are permanent poles. Now the ship which I showed you in the previous slide, the lines of force were entering on the deck and they were leaving out from the keel. So if there is a bulkhead, let us say you are welding a bulkhead in place, intertank bulkhead, the topmost part of the bulkhead is going to acquire blue polarity and the bottommost part of the bulkhead is going to acquire red polarity, and these poles will remain permanent always, as they are permanent magnetism. The vessel is going to acquire magnetism both in the horizontal and vertical planes. I will explain this to you with the help of diagrams going further. A blue pole is acquired where the lines enter the material, and a red pole is acquired where the lines of force leave the material. Now, as I told you that this permanent magnetism is acquired both in the horizontal direction and the vertical direction. Now, let's try to understand that by making some diagrams. Let us assume that we have a ship being built at a yard which is on the equator. We have a yard somewhere on the equator and the ship is being built. Two ships are being built there. One of the ships is put in the yard heading in the southerly direction. So right now you see where my laser pointer is. This ship is being built in the yard on a southerly heading. This is how the orientation of the yard is. Now, if it is being built on a southerly heading, you see a red color pole here at the bottom or at the south. This is basically the south pole or the south magnetic pole of the Earth. And you see a blue pole at the top or north of the ship. This represents the north magnetic pole of the Earth, which has the blue polarity. And these dotted lines which you see, the dotted lines going from red pole to the blue pole, they represent the magnetic field lines of the Earth. We are aware that magnetic field lines come out of the red pole, which is the south magnetic pole of the Earth. They are all coming out from the red pole, and these lines of force, they re-enter or go into the blue pole or the north magnetic pole of the Earth. So that is why you see the arrows are always from red to blue. Now this magnetic field is affecting the ship which is being built. And all these magnetic field lines, they are entering into the ship structure from the bow side, giving it a blue polarity, and they are leaving out from the ship from the stern side, giving it a red polarity. Why the bow is blue in this case? Because wherever the magnetic field lines enter, that is the blue pole. And why is the stern red in this place? The stern is red because wherever the lines of force come out, that is the red pole of the magnet. So with the lines of force entering into the bow, it gets a blue polarity. And with the lines of force coming out of the stern, it gets a red polarity. Now, let's assume that there is another ship which is being built in the same yard, but in a different dock. And that dock has a northeasterly orientation. So you now concentrate on the ship on the right side. This ship is heading in a northeasterly direction. The south pole of the Earth is at the same location. North pole is at the same location. Magnetic lines of force of the Earth are moving in the same orientation from south to north. But with the ship heading in the northeasterly direction, now if you look carefully, the magnetic field lines are entering into the ship structure from the starboard quarter side. So you see, starboard quarter is where the lines of force are entering, and that is where a blue pole will be acquired. These lines of force are coming out of the ship structure from the port bow, and that is where a red pole will be acquired. So you compare both these ships now, you see with the change in heading of the ship, the horizontal positioning or location of the poles has also changed. So is this part clear, beta? Any doubts coming in? Very good, beta. Great. Okay. So next is permanent magnetism in the vertical orientation. Now, before we go there, would you like to have a break, beta? 5 minutes break?
Sir, break there, sir.
Okay, all right. So let's go for a break. After the break, we will continue. We will see the vertical magnetism. So let's meet back after 5 minutes, beta.
Thank you, sir.
Okay, बेटा आगे वापस.
हाँ जी सर आगे.
Okay, good. So let's go back to the presentation. Okay, so we saw beta the permanent magnetism or the permanent poles are acquired on the ship structure, and the horizontal positioning of the poles depends upon the heading of the ship when it was built. Now let us see what decides the vertical positioning of the poles. Let's see. Now let's see the vertical positioning of the poles of the permanent magnetism of the ship. Now for this, let's make another diagram. In this diagram, you can see the Earth, and in the Earth we can see the north magnetic pole, which is blue, represented here, and you can see the south magnetic pole, which is red, represented here. And you see the dotted line also representing the magnetic field lines of the Earth. You can see from the red pole the lines are coming out and the lines are re-entering into the Earth's surface at the blue pole. Now let's assume a ship which is built in the northern hemisphere. You see these two ships on the top. This one is built on the northern hemisphere, at some place on the northern hemisphere. This ship also is built in the northern hemisphere. This ship is being built in the yard, somewhere located in the northerly latitudes. Now you see that when the ship is being built, the magnetic lines of force will be coming into the Earth's surface. So they will be entering from the deck of the ship and they will be coming out or leaving out the ship from the keel. So since they are entering into the deck of the ship, it will acquire a blue polarity. And since they are leaving out or coming out from the keel of the ship, it will acquire a red polarity. This is exactly the same situation for which I showed you the diagram in the previous slides also. We saw a ship standing in a yard and the magnetic field lines were going vertically downwards. So they were entering from the deck, giving it a blue polarity, and they are coming out from the keel, giving it a red polarity. So if the ship is built anywhere in the northern hemisphere, it will have a blue polarity deck and a red polarity keel of the ship. Now let's visualize a ship being built somewhere in the southern hemisphere. So this is the ship you see being built in the southern hemisphere. Now in the southern hemisphere, we are aware that the lines of force come out of the Earth's surface. So you see the lines of force coming out of the Earth's surface will enter from the keel of the ship, giving it a blue polarity, and they will come out from the deck of the ship, giving it a red polarity. So any ship which is built in the southern hemisphere will have a blue keel and a red deck. Any ship built in the northern hemisphere will have a red keel and a blue deck. So when you come to know the location where the ship is built and the heading on which the ship is built, you can find out easily what is the vertical and horizontal positioning of the poles. So the same thing is mentioned here. vertical positioning of the poles depends upon the hemisphere where the vessel is built. Clear, beta? Any doubts? Very good, beta. Great. Now we have understood that depending on the heading of the ship and the hemisphere in which the ship is built, the positioning of the permanent pole could result in any oblique direction. The permanent magnetism vector could be present in a three-dimensional orientation. You can understand it from this particular diagram. We have this particular ship here, and the permanent magnetism is represented by this oblique slanting vector. This vector represents the permanent magnetism of the ship. One of the poles is on the deck towards the port quarter, and other pole is at the keel towards the starboard bow. So this vector represents the permanent magnetism of the ship. Now to counter this permanent magnetism, to rectify it, to correct it, this permanent magnetism in any oblique direction is split up into three mutually perpendicular directions. We resolve it, or we split this oblique vector in three mutually perpendicular directions. One of the component is split in the fore and aft direction. You can see this is the component in the fore and aft direction. This is known as the fore and aft component of the ship's permanent magnetism, and it is represented by alphabet P, Papa. Then you see this second vector, this is the second component. This is the athwartship component of the ship's permanent magnetism, and it is represented by Q, cubic. And the third component is the vertical component. You can see this particular arrow shows the vertical component of the ship's magnetism. This is known as the vertical component, also called as the heeling component, represented by alphabet R, Romeo. Now, why are we breaking it up into three vectors like these? This is because it is very difficult to counter the permanent magnetism in an oblique direction in any 3D orientation. But when you split it up in three mutually perpendicular directions, that is fore and aft, athwartship, and vertical, it becomes easy for us to counter all these three components one by one. When we do the compass correction, we will see how this fore and aft component is corrected. Then we will see how this athwartship component is corrected, and we will also see how the vertical component is corrected.
Sir, there is no horizontal component we saw earlier, H and Z. They are not into force here.
Beta, the horizontal and vertical component, HF and Z, they were the different components of the Earth's magnetic field, beta. वो अर्थ के मैग्नेटिक फील्ड के कंपोनेंट्स थे. जो ये कंपोनेंट हमने बनाए हैं PQR, these are the components of the ship's permanent magnetism.
Okay, understood, sir.
Okay. Great. Let's move ahead.
सर ये इंड्यूस्ड जो मैग्नेटिज्म है, जो सॉफ्ट आयरन मैग्नेटिज्म है, उसका भी एंगल कुछ ऑब्लिक ही रहेगा ना वैसे तो?
नहीं बेटा, उसका एंगल ऑब्लिक नहीं रहेगा. द रीजन इज दैट इंड्यूस्ड मैग्नेटिज्म इज जनरेटेड इन शिप स्ट्रक्चर्स. शिप स्ट्रक्चर विल ईदर बी हॉरिजॉन्टल और वर्टिकल. सो जहाज के जो स्ट्रक्चर हैं, फोर एंड आफ्ट, लॉन्जिट्यूडनल, आउटवर्ड शिप बीम और वर्टिकल स्टिफनर्स, उनकी ओरिएंटेशन तो फिक्स है. शिप में वी डू नॉट हैव ए ऑब्लिक स्ट्रक्चर which is going from, let us say, port quarter to starboard bow. So that's why the induced magnetism is generated in linear directions. It will be either horizontal fore and aft, or horizontal athwart ship, or vertical.
ठीक है सर.
Okay. Now coming to the concept of compass work. Correcting a compass is also known as compass work. So what is the concept behind it? Permanent magnetism and induced magnetism both cause deviation of the magnetic compass. Now, as I told you, if our magnetic compass is affected solely by the magnetic field of the Earth, it will give us precisely the magnetic directions. Once you have the magnetic directions, you can apply the variation. Variation can be easily picked up from the chart and applied. And once applied, it gives you the true directions. But if you have the magnetism of the ship, permanent or induced, it will disturb our compass, and that disturbance is known as deviation. The permanent magnetism can be easily understood by considering its three components or by breaking it up into three components. That is the P component, which is in the fore and aft direction, this one. Then the Q component, which is in the outward ship direction, and the R component, which is in the vertical direction. So once you understand these three components of the permanent magnetism, we can cancel it or counteract it one by one. The induced magnetism can also be generated in three different directions. It can be broken up into three different directions. You can have the induced magnetism generated in the fore and aft direction. In fore and aft horizontal soft iron. That could be a fore and aft longitudinal. This is one orientation in which induced magnetism can be generated. Induced magnetism can also be generated in the outward ship direction, in outward ship soft iron, which could be the transverse or the outward ship beams, and it can be generated in the vertical direction, which happens in vertical soft iron. Examples of vertical soft iron are masts, cranes, or funnels, or vertical stiffeners. Now, each of these components has to be treated separately. You see, permanent magnetism, three component, fore and aft component, outward ship component, vertical component, and induced magnetism in fore and aft structures, horizontal fore and aft structures, induced magnetism in horizontal outward ship structures, and induced magnetism in vertical structures. They all have to be treated separately. There are 6 total components of the ship's magnetism which affect our compass. They need to be treated separately as the deviations which they generate varies with change in heading, change in latitude, and change in hemisphere. When the heading of the ship changes, it is possible out of these 6, some of the vectors, some of the components may be changing, whereas some may remain fixed or constant. It may happen with change in latitude also, it may happen with change in the hemisphere also. So since all of them are changing differently from each other, they have to be compensated differently in such a way that as and when the components of the magnetism change, our correction also changes in the same way. Because whatever correction we do to our compass, that correction should be able to cancel out these components in any condition. If the ship is heading in a fore and aft orientation, the fore and aft longitudinal is the most powerful. It is magnetized by the Earth's magnetic field. So we should have a corrector which should be able to judge this and provide a correction in the fore and aft direction of the same amount. Now when the ship goes to a easterly course, the fore and aft longitudinal loses its entire magnetism. Induced magnetism is lost. So our corrector should be such that it senses that the fore and aft longitudinal has now become powerless, and the correction which it was providing is also brought to 0. So we need a correction mechanism for each of these components, treating them separately, and it should be such a mechanism which keeps on changing its correction depending upon the change in the permanent or induced magnetism of the ship. This is what we call as component, the compass work. Now for treating these components, the deviation of the compass is divided into 5 different parts which we know as coefficients. So as I told you, we need to tackle these components separately one by one. So therefore, how do we tackle them differently? By dividing the deviation of the ship into 5 different parts. These parts are known as coefficients. Now, what are these coefficients? These coefficients are named as A, B, C, D, and E. The first 5 alphabets, A, B, C, D, and E. This is how the coefficients are named. So beta, any doubts coming up to here? Okay, great. Now let me take you a little more deeper into these coefficients, and let's try to understand how this deviation is broken up into 5 different parts. What is the criteria, how it is broken up? So let's try to see that. Now this is very, very important. Once you understand the concept behind these coefficients, further explanation of coefficients becomes simple and easy. So let's try to see that better. It must be clearly understood that these coefficients are the deviations generated or parts of the deviation generated, and these are not the forces causing deviations. The forces which were causing deviations are the permanent magnetism, understood by breaking it down into 3 components: P component in the fore and aft direction, Q component in the authwardship direction, and R component in the vertical direction. And the second force causing deviation is the induced magnetism of the ship. Induced magnetism is generated in horizontal soft iron. It may be in fore and aft or authwardship direction, and induced magnetism is generated in vertical soft iron. This permanent and induced magnetism of the ship is the force which is causing the deviation. The coefficients, on the other hand, are different parts of deviation. Now, how are these parts formed? To give you an example, let us say on a particular heading, the ship has a deviation of 10 degrees east. Now we will break down this 10 degree east into different parts. Like you can say one part is 1 degree east, second part is 3 degrees east, 2 degrees east, 3 degrees east, and 1 degree east. These parts are known as coefficients. Let us now try to understand what these coefficients are. We know that whenever the ship's head changes, the deviation also changes. But the change in the heading may affect different parts of deviation, what we call coefficients, in different ways. I'll repeat. The change in the heading of the ship may affect different parts of deviation, what we call coefficients, in different ways. Say for example, out of this 10 degrees east, we have a 1 degree east deviation which is independent of the ship's head. Irrespective of what is the heading of the ship, the contribution of this part remains 1 degree east only. There could be another part of deviation which may be 0 on northerly heading and may become maximum on easterly heading. And it may become 0 again when the ship goes on a southerly heading. So the change in heading affects these parts differently, which we call as coefficients. Now, if we know all the coefficients, the total deviation can be calculated by using this formula. That is, deviation is equal to coefficient A plus coefficient B multiplied by sine of course plus coefficient C multiplied by cos of course plus coefficient D delta multiplied by sine of twice the compass course plus coefficient echo multiplied by cos of twice the compass course. Now, as I gave you an example, that there could be certain part of deviation which is not affected by the ship's head. You see, the coefficient A is such a part or component of deviation which is not connected with the heading of the ship or the course of the ship. Irrespective of whichever course the ship is on or whatever is the heading of the ship, the contribution of coefficient A always remains the same. Whereas, if you look at coefficient Bravo, you will observe that if the heading of the ship is 0, the contribution of Bravo also becomes 0 as sine of 0 is 0. If the heading of the ship becomes 90 degrees, the coefficient B contribution becomes maximum because sine 90 has a maximum value of 1, giving a big value to this second component of the ship's deviation. If you look at the third part, you will see on a northerly or southerly heading, 0, 0, 0 heading, this coefficient will give the maximum contribution to deviation. Because on 0 heading, cos of 0 has the maximum value, which is 1. So this part gives the maximum contribution to the total deviation. However, when the ship goes on a easterly course, cos of 90, 090 becomes 0. The contribution of this third part or coefficient C also becomes 0. So this is how the deviation is broken up into 5 different parts: Alpha, Bravo, Charlie, Delta, and Echo. And if we know all the parts, we can easily calculate the total deviation on any heading. So beta, are you able to understand that? Any doubts coming in? Okay, all right. So let me close this presentation. This particular topic is covered up. We have done the ship's magnetism. So I'm closing this down now, beta.
Sir, this how to get the value of coefficient, sir? This will be covering in the next slide, sir.
Yeah, that's right, beta.
Okay,
अब ये जो 5 coefficients हमने देखे हैं, इनमें हम individually जाएंगे. We will enter into each one of these coefficients, starting with A, B, C, D, and E. And we will see what are the causing factors of this coefficient. And for every coefficient, there is a deviation diagram which is made. So we will be making that deviation diagram. So how that deviation is generated, we will understand that. And we will also see the correction of the coefficient. How is that particular coefficient corrected? There are different correctors which are fitted in the magnetic compass. You see, you may have magnets fitted in the fore and aft direction. There are some magnets which are fitted in the outward ship direction. Then you have the soft iron spheres on both the sides in the outward ship direction. You have a cylinder bar, which is forward of the pinnacle. And you have a healing error bucket, which is exactly below the compass, fitted with a chain and pulley. So all these correctors are there, and they are correcting the different coefficients. So we will now go into each one of them and see in detail how they are generated, how they are corrected, how to make their deviation diagrams. ये one by one अब देखेंगे. जो हमारे पेपर में क्वेश्चंस आते हैं, अब बेटा उसमें जो पहला क्वेश्चन आता है जो हमने अभी तक कवर किया है, द फर्स्ट क्वेश्चन इज एक्सप्लेन द मैग्नेटिज्म ऑफ द अर्थ. Okay, the second question which comes in, explain the magnetism of the ship. What do you understand by hard iron and soft iron? And what do you understand by components PQR, related to the permanent magnetism of the ship. And what do you understand by HSI, VSI? These coefficients related to the induced magnetism of the ship. So ये पहले दो क्वेश्चन हैं जो हमने अभी तक कवर किए हैं. अब बेटा आगे each of the coefficients alpha, bravo, charlie, delta, echo, you can get a 25 marks question on each coefficients. So a simple question, explain coefficient A, could be a full 25 marks question. So you will need to explain what is coefficient A, make a deviation diagram, and explain the correction procedure. So this is what we will be doing now.
Okay, sir. Okay, sir. Understood, sir. Thank you, sir.
Okay.
Sir,
bolo beta.
As you said, that there'll be 6 directions in which the induced and permanent magnet will be affecting the deviation. Right. So the directions are 6, but the coefficients are only 5. Why is that?
Okay, beta. Now you see, beta, जो coefficients बनाने का criteria है, that is not as per the directions. Coefficient बनाने का criteria अलग है. Okay. Coefficient A का एक criteria है कि it consists of that deviation which remain fixed on all the headings. You take the ship on any of the heading, the coefficient A contribution will not change. Okay, so ये दोनों क्राइटेरिया अलग अलग होने की वजह से जो हमारे कंट्रीब्यूटिंग फैक्टर्स थे, जो फोर्सेस जनरेट कर रही हैं डेविएशन को, P, Q and R of permanent magnetism and 4.5 longitudinal HSI, outward ship beam HSI and vertical soft iron VSI, ये फोर्सेस तो 6 थी टोटल, लेकिन हमारे कोफिशिएंट्स 5 ही हैं क्योंकि क्राइटेरिया अलग हो गया. जब हम ये डिस्कस करेंगे देन यू विल अंडरस्टैंड. अब जैसे बेटा जो हमारा कोफिशिएंट ए है, इट इज नॉट जनरेटेड विद वन स्ट्रक्चर, इट इज जनरेटेड बाय ए कॉम्बिनेशन ऑफ 4.5 सॉफ्ट आयरन एंड ऑथवर्ड शिप सॉफ्ट आयरन. ये दोनों के कॉम्बिनेशन से जनरेट होता है.
Okay, understood. So they are not fully related. Only yes. The coefficients can be a group of some directions and others.
That's right, beta. That's right. हाँ, और बताओ बेटा, और doubts?
Sir, what about 9 rod concepts?
Okay. बेटा ये जो 9 rods हैं, basically जैसा हमने अभी देखा that the soft iron structures can be divided into 3 kind of structures. You have a 4.5 horizontal soft iron, you have a outward ship horizontal soft iron and you have a vertical soft iron. Right बेटा? अब ये जो structures हैं बेटा, ये हमारी कंपास के starboard में भी हो सकते हैं, port में भी हो सकते हैं. So basis their location, अगर ये सॉफ्ट आयरन हमारी कंपास के अलग अलग लोकेशन में हमें मिले तो हमने उसको रिप्रेजेंट करने के लिए ना रॉड्स का नाम दे दिया. ओके, रॉड्स लाइक से फॉर एग्जांपल यू हैव अ वर्टिकल स्ट्रक्चर विच इज एग्जैक्टली बिलो द कंपास. ओके, सो हमने उसको एक पर्टिकुलर नाम दे दिया. ओके, लेट अस से जस्ट टू गिव यू एन एग्जांपल ई रॉड. ओके, तो जब हम उसको रेफर करेंगे तो हमें एक्सप्लेन करने की जरूरत नहीं है. अगर हमने ई रॉड बोल दिया तो दैट मीन्स दिस पर्टिकुलर काइंड ऑफ स्ट्रक्चर. सो इट इज जस्ट ए नॉमेनक्लेचर विच इज गिवन टू आइडेंटिफाई डिफरेंट स्ट्रक्चर्स ऑन बोर्ड. ओके, मैं आपके साथ एक डायग्राम शेयर कर दूंगा.
Structures are induced type or permanent type?
Say again बेटा.
These structures, what you are saying, 9 rods concept, in that these structures are permanent or induced type?
They are all soft iron structure and they will have induced magnetism beta. Okay, none of them is a hard iron permanent magnet. All these 9 rods, they refer to soft iron structures and they will have induced magnetism. Right beta? Clear? ओके, जस्ट गिव मी अ मिनट. मैं ये 9 रॉड्स की जो डायग्राम है ना, ये अभी आपको भेज ही देता हूँ. ओके, आई विल हैव टू लुक फॉर इट. नो इश्यूज, आई विल पोस्ट इट ऑन योर व्हाट्सएप ग्रुप so you can have a look. Sometime you may get a direct question. Okay, not a full 25 marks but a 10 marks question. explain the 9 rods. So you will have to make the diagram and explain those 9 rods. Basically, you have to mug them up. Okay. Give me a minute. I'll show you here. Okay, beta. Here it is. So can you see the screen now, beta? So you see these are the 9 rods. These are the rods which are lying in the fore and aft orientation. These are rods lying in the outward shape orientation, and these are vertical rods. So A rod is basically a rod which is in the fore and aft orientation passing through the compass location. Okay. B rod is a outward ship direction horizontal soft iron, which is either forward or aft of the compass in port or starboard orientation. It is only present on one side of the compass, not on the other side. C rod is a vertical rod, which is forward or aft of the compass. So like that, you have 9 rods, beta. A, B, C, D, E, F, G, H, K. I is missing. So I rod is not there because I can be mistaken with 1. So that's why I has missed out.
Sir, in rod system also color combination red and blue?
No, beta. Rods only refer to the structures. Now, what kind of magnetism will be present in that structure? That's a separate issue. Okay. Because you have a vertical rod. If you take the ship in northern hemisphere, you will have different poles. If you take the same ship to southern hemisphere, you will have different poles. So which poles are generated? That's a totally different thing. The rods only refer to these structures.
Okay, sir.
Okay. All right. Closing this down now, beta. I'll share this diagram on your group. ओके और बताओ बेटा और क्या डाउट्स आ रहे हैं?
डाउट तो जो पास होने वाला है वो सब पहले भेज दो सर, हम लोग पढ़ते रहेंगे.
ओके ऑल राइट. मैं आज आपको भेज दूंगा बेटा. आई विल सेंड यू द नोट्स. जो हमारा आगे आने वाला है, कोफिशिएंट्स आने वाले हैं, उनका भी समरी आपको मिल जाएगा. एंड you can start to go through as we cover up the topics. You can start to go through those notes slowly. Okay, magnetism is a huge. अगर आप वो मैं भेज देता हूँ आज बेटा, भेज देता हूँ आपको. ओके, इट्स ए ह्यूज टॉपिक. सो अभी हमने सिर्फ पहला पार्ट जो है वो टच किया है. द नेक्स्ट पार्ट इज द मेजर पार्ट विच आर द कोफिशिएंट्स. सो ये 5 कोफिशिएंट टच करेंगे. आफ्टर द कोफिशिएंट्स देन वी विल हैव द compass error. There's a healing error and compass correction. So these are the 2 topics which will come towards the end. Okay, अब मुझे एक बात बताओ बेटा. We have some time left. Do you have the allege to go into coefficient A?
No, sir.
Okay, all right. ठीक है.
तो मना करने में शर्म आ रही है, बट सही में नहीं बचा सर.
ओके ऑल राइट बेटा. ओके नो इश्यूज. ठीक है, आई कैन अंडरस्टैंड. बिकॉज ये टॉपिक अगर नॉर्मल क्लासरूम लेक्चर्स होते तो यही कम से कम 2-3 सेशन में कवर होता, जो आज आपने अंडरस्टैंड किया है. बट टेल मी वन थिंग फ्रैंकली, वर यू एबल टू अंडरस्टैंड द कॉन्सेप्ट बिहाइंड द कोफिशिएंट्स?
हाँ सर, वो समझ आ गया.
ये सर, बट सर बेटर होगा आप ये अगर ये स्लाइड्स अगर भेज दोगे ना, जस्ट वी विल गो थ्रू वन टाइम, सो वी विल गेट मोस्ट बेटर अंडरस्टैंडिंग ऑन दिस.
Okay, no problem. I'll send you in a PDF format so you can go through that. I'll send you the notes today.
Thank you.
Okay, all right. So आज के लिए फिर हम यहीं रुकते हैं बेटा. We have covered the ship's magnetism and tomorrow we will be going into the coefficients starting with coefficient A. Hopefully we will be able to cover at least 1.5 and if we could pick up speed maybe 2. Alpha and Bravo hopefully we should be able to cover tomorrow. Great. So
can I ask plotting question?
बोलो बेटा.
So in most of the questions, there is a part of reporting the target. So can we standardize a table so that we don't miss anything? Because somewhere it's mentioned in the sheet, in the book radar, there are so many things like range increasing bearing. So what to report and what not to report when we are writing the answer?
Okay बेटा. जो चीज़ों में आपको डाउट आ रहा है ना, one is the bearing is opening up or closing in, another is the range is increasing or decreasing, उनको छोड़ दो. Okay. And the standard items, what is the course of the target, what is the speed of the target, what is the CPA, what is the TCPA, and what is the aspect. These are the standard items which we report.
Okay, sir. So basically CPA, TCPA, course, speed, aspect, 5 things.
That's right. That's right, beta.
Okay. And for exam, what is the margin of error? Because if we change the scale, the answer changes by 3 degree, 4 degree sometimes. So what is the accepted margin?
Okay, बेटा. देखो ऐसा कोई recommended या set margin of error नहीं है because the amount of error will depend upon what scale you have picked up. If 1 centimeter 1 mile लिया है तो error would be less. 1 centimeter 2 mile लिया है, the error is going to become double. So every examiner knows about this. So what is important is that your plot should be fundamentally correct. It is exactly like chart work. When you do chart work questions, your answers will never match exactly with the book answers. So a little bit of difference is fine. And there is no definition of a how much is little bit and how much is excessive. So you concentrate on making the plot fundamentally correct, and that should be fine, beta.
Okay, sir. And sir, can you just give a rough idea on the last question of the exercise you sent? The last question.
Okay. अभी pick up कर लेते हैं बेटा. Let me open up. I'll open it up here.
Do we need to show this working, sir, for this TCPA aspect, everything in the answer sheet? Or it's okay if we write it down directly, calculate in the rough and write it directly?
Beta, when you make the plot, CPA will be directly picked up. The CPA range will be directly picked up from the plot, and you will write as picked up from the plot, CPA range is so and so. Okay. When you calculate the TCPA, what you will pick up from the plot is the target's distance in 12 minutes or whatever is the plotting interval. So उसकी interpolation आपको दिखानी है एक step में.
Okay, sir.
Okay. Okay, all right. Let me open up the exercise beta. Give me a minute. Okay, beta. So here is the exercise. Which question do you want to ask, beta?
Sir, the solved questions you sent yesterday in that file.
Okay. That file. Okay, all right. Give me a minute.
Sir, if you want, I'll send the screenshot of that question.
No, just give me a minute. I'll open up. Okay, here it is. Right, beta. Which question, beta?
The absolutely last one.
Okay, all right. Let's see the last one. Okay. Own vessel's course is 050. Speed is 12 knots. Following observation made on the radar screen. Target A is 0509 miles, 9 miles, 7 miles, and 5 miles. So the bearing is not changing. Target B is a light vessel, 080, 6 miles, 087, 097. Report both at 0812. At 0812, A and own vessel decide to alter course to their respective starboard. Okay. If target A alters course by 10 degrees, calculate the alteration required by own vessel in order to comply with the master standing order of 2 miles CPA with all passing traffic. Okay. Okay बेटा, इसमें कहाँ पे डाउट आ रहा है बेटा?
So once we for target A, we alter by 10 degree at 0812. So can we, like, how should we do it? Should we transfer the vectors from AOW to the new position, or do it only in that triangle only?
ओके ऑल राइट, मैं समझ गया बेटा इसमें डाउट कहाँ आ रहा है. बेसिकली इसमें टारगेट हैज ऑल्टर्ड इट्स कोर्स, सो हाउ टू शो द टारगेट्स ऑल्टरेशन, राइट? सो लेट मी डू वन थिंग बेटा, लेट मी सेंड द सोल्यूशन टू यू. मैं व्हाट्सएप ग्रुप पे आपको इसका सोल्यूशन भेजता हूँ.
ओके सर,
फॉरगेट अबाउट दिस. मैं आपको व्हाट्सएप ग्रुप में इसका सोल्यूशन भेजता हूँ. So you will get it on the group. Give me some time.
Okay, sir. And sir, sorry to bother. One more thing about the head reach.
Right.
Like I could not understand properly the head reach concept.
Okay, all
so
right.
Just
all right.
basic idea if you can give us.
No issues. मैं आपको head reach की definition जो है ना ये भी भेजता हूँ बेटा. Just read it. You will understand it. If doubts are still there, ask me again in the class tomorrow.
Okay.
Okay. So this particular numerical and head reach. All right. Okay, beta. Any more doubts? Okay, all right. So shall we close out for today, beta?
Sir, it's not the doubt. Sir, what can be the last date of the class, sir?
बेटा अभी तो नहीं बोल सकते हैं so early, but we should be completing well within the schedule.
Okay, till next month 6th.
Just have a look at the scheduled classes. We should be able to finish well before that.
Okay, sir. Okay, thank you.
Okay, all right. So let's break off for today, beta. I will see you tomorrow and we'll continue. Bye-bye.
Bye, sir. Good night, sir.
Okay, beta. Bye-bye. Good night.